Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Welcome, everybody. I'm going to share our class splash screen here momentarily. And Lee is not able to join us, and I keep forgetting to ask her for what she reads at the beginning. So forgive me that you're just getting me, but we are on Wednesday. It is September the 11th. So I know I'm not alone in remembering all that this day means, but we are praising God that He is still sovereign even on those dark days. And so today we're going to talk about exponentiation. So you might notice if you've been following along each week that this is our first week where there's nothing written on the math map page. So Lee had included some notes on that page as sort of sample ideas of the kinds of things that you or your student might want to take note of. And now you just have a blank page. So this is intended again as a place for you to take notes each week. Your student can take notes in community of things they want to remember to talk about at home, or you as a parent can use this to take notes for things you may want to come back and revisit the following year. So take a minute and look at your math map and identify where you are. So we are all on exponentiation. So this row, and then whatever domain you are using at home, go ahead and follow that down. So I am using the complex. So I'm going to put my check mark in that box that is the complex exponentiation. And just to emphasize again, if you haven't been following along, right, we can be in any of those domains, and we're going to see the same concepts in roughly the same order with similar problems. And so that's how the scaffolding works from year to year. It's this gradual ramp up to looking at those complex ideas, starting with very simple numbers and simple operations that we're asking students to do, and ramping up to being able to do them independently. So we're not there yet in complex. We've got a little ways to go, but that's the idea of how those domains are going to help us to scaffold the concepts. So we're going to start our time with a little bit of national number knockout, N2K. So I've started our timer, and our numbers are 5, 4, and 3. So go ahead and let me know what numbers you're knocking off the board.
12. 5 plus 4 plus 3 is 12.
Yeah, 5 plus 4 minus 3 is 6.
29. 5 times 4 is 20, plus 3 squared is 29.
5 to the 0 plus 4 to the 0 plus 3 to the 0 is 3.
3 times 4 plus 5 is 17.
5 to the 0, 4 to the 0 times 4 to the 0 times 3 to the 0 is 1.
5 squared is 25, plus 4 is 29, plus 3 is 32.
5 times 4 is 20, plus 3 is 23.
4 plus 3 is 7, minus 5 is 2.
5 minus 4 plus 3 is 4.
4 squared plus 3 times 5. I guess you need parentheses. 31.
4 to the 1/2 power is 2, plus 3 equals 5 times 5 to the 0 power is 5.
Nicely done.
4 squared is 16 plus 5 plus 3 is 24.
3 cubed plus 4 plus 5 is 36.
4 squared is 16, minus 5 is 11, plus 3 is 14.
5 minus 4 plus 3 squared is 10.
Great job.
5 squared minus 4 to the 1/2 is 23 times 3 to the 0.
All right.
Minus 2 to 0 is 22.
All right. That's it. I'm going to cut you off, but well done. All right, well, let's go ahead and take some time. I think this is one of Lee's favorite pieces of art. I think it may have been one of the original pieces of art in the early days of the math map as we went through and were looking for artwork. And this was one that has persisted from the very beginning, that Lee really enjoyed this one for this week. And early on used this as one of her illustrations for how she hopes that the artwork is going to provide a memory peg for our students, that they're going to remember that exponentiation and bunnies went together. And so she, that when students are thinking throughout the year, that artwork is going to give them a peg to help them remember what was in each booklet. And this is one of her favorite examples. So let's go ahead and open it up to what do you guys see? And specifically think about how might this relate to exponentiation.
Bunnies reproduce.
And they reproduce quickly. It's a very short pregnancy and they're prolific at it.
Yeah, this sort of leads to a birds and bees discussion, but it's very amazing how many bunnies can come from 2 bunnies so fast.
I think the same is true about the wildflowers. So I just moved to Texas and their state flowers, the bluebonnets. So that's what I keep thinking about and how they reproduce.
We love our bluebonnets. Also with the bunnies, you can just think of just squared. For every bunny, there's 2 ears that stick up. So you can easily talk about squares that way.
Okay. Now keep in mind that only works, squaring and times 2 only works if your base is 2. Lee and I just had this conversation the other day that when we square something, it's not always a doubling. But when our base is 2, then it is a doubling, right? So just to keep that in mind.
I was thinking about the fact that the little girl is feeding them, which is giving them the energy or the power to reproduce, so that there's some kind of power thing happening there.
I like that.
Oh, I think of how smiles are contagious and exponentiate.
I like that.
And it's such a peaceful picture, which I think in math, we don't always exude that peace, but it sort of gives hope that in the exponentiation, it's going to be okay.
It's a great point. Well, thanks, Christine. I don't know if you guys saw that in the chat log. She put in there that female rabbits have 2 uteruses, so they can have 2 pregnancies at the same time. So how many people want to sign up for that? Can you imagine?
Now my questions are exponentially growing after that comment.
So let's take a look at our reflection today from Barnabas, and it's, "O Lord God Almighty, who didst endue thy holy apostle Barnabas with singular gifts of the Holy Ghost, leave us not, we beseech thee, destitute of thy manifold gifts, nor yet of grace to use them always to thy honor and glory through Jesus Christ our Lord. Amen." What word in there might pop out to you as something to do with exponentiation?
Manifold?
Manifold, yeah. So when we think, if you think of that as being many folds, folds are kind of a base 2. If I have a piece of paper, right, and there's 0 folds, right, I just have one section. If I fold it, I have, right, so now my base is 2. The first power of 2, I have 1 fold. There's now 2 sections. I didn't really think about this when I started using my hands, right? So let me go this way. So now if I could somehow fold that in half, right, I have 2 folds, but I now have 1, 2, 3, 4 sections, and I can't fold my hands any more than that. But you can see where we would be going. If I folded that again, I'd have 8 sections. So this idea of many folds, right, gives us this idea of doubling. And so when we think of God's manifold, right, manifold gifts, are we talking about just a couple of gifts? Or a lot of gifts?
A lot.
A lot.
A lot, right? So when we hear that word manifold, we're thinking that we're getting to be a big number. And that's what exponentiation does, is it gets big. Right, it may start off gradual, but then all of a sudden it gets big really quickly. And so when we think about, you know, God's gifting, right, we may think, oh, there's these little gifts. And then as we start to use them, and he takes that and multiplies it, right, in this manifold way, our gifts grow, right? Or maybe the gifts themselves don't grow, but the impact that those gifts can have grows. Kind of like whoever it was that said about a smile, right? That if we smile at somebody, right, let's say I smile at 2 people, and then they each turn around and smile at 2 people, right? That gift of the smile that I gave to somebody, right, throughout the day could be, right, 100 people or more, depending on how many people turn around and share that gift of a smile. And so God can take our gift, and it becomes exponentially greater as it moves away from us, as we take the gifts he's given us and give them back to him, right? He just makes that so much greater. Are there any last thoughts that you would like to share about this artwork, or the title, or reflection, or the quote?
I think maybe there's less conversation this week because of what Albert Bartlett says. It's just this is a lot harder to wrap your brain around.
It is, and because we don't, I mean, beyond the exponential function, the other idea about our human brains, right, is we don't really comprehend things that are really, really big, nor do we comprehend things that are really, really small. Our scale of comprehension is fairly limited, and so that's why we'll try to put really big things into the context of something else. Similarly, when we talk about probabilities, we don't have a good innate sense of probability. We tend to overestimate or underestimate probabilities all the time, and so maybe it's just a good humility moment to recognize, right, that there's, yes, that as Tanya says, that God's thoughts truly are higher than ours.
And I also realized there are 12 bunnies there and 1 girl, and God needed 12 disciples to change the world. He just started out the 12, so there's some connection there too.
Oh, I love that. I have not seen that before, but I really, really like that. That is great. All right, well, let's go ahead and take a look at our I² page. And as we look at this, there's lots of things that we could look at here, but I'm going to go ahead and let's talk about definition this week. So what are some things on here that you might like to have defined?
I'd like to have logarithmic scale defined.
And almost any of the words in bold: power, root, vectors, linear scales, constant difference, intervals, logarithmic scales, constant ratio, power.
So let's take a minute and pick one of those. Let's go ahead and let's use logarithmic and linear scales because that's the title of this particular invention page. And there's some things we could read off of here. So what would be the definition of a linear scale?
Have a constant difference between intervals.
Okay. And so we read that. And so let's go ahead and who wants to tell us what the definition of a logarithmic scale is?
Constant ratio between intervals.
So we've just defined them. Let's use our skill of comparison now to see if we can maybe get a little bit more of a sense of what that means. So we have three examples of each, right? 3 examples of a linear scale and 3 examples of a logarithmic scale. So as you look at that linear scale, do those scales feel familiar to you or unfamiliar to you?
Familiar.
They feel pretty familiar. Those are what we're probably the most used to seeing. What are some things in your everyday life that would have a linear scale on them? What kinds of measuring tools might you use?
Ruler.
Good.
Liquid measuring cup.
Good.
Thermometer.
Thermometer. Good. So we see graduated cylinder. Good. So we see a lot of things that we're used to using, we use linear scales for. Now let's go ahead and look at those 3 scales for the logarithmic scales. Are they familiar or unfamiliar?
A little bit of both. It's familiar in that I recognize 110, 100, 1000, and then 1, 8, 64, 512. But then it's unfamiliar in that it's on a linear, it's drawn this way or presented this way.
Right, because is the distance between 100 and 1000 the same as the distance between 1000 and 10,000?
No.
Oh.
No, that distance is different, right? So does anybody happen to have a logarithmic ruler at home?
No.
Would that even work?
No.
Not for measuring.
Not for measuring, right? So if I wanted to measure my desk and I tried to use a logarithmic ruler, it would cause some confusion, wouldn't it? Does anybody
Yes.
know of any logarithmic scales that you may have heard of or have used?
I remember during when COVID was first a thing, they had like the CDC or somebody had a thing that showed a logarithmic, like what the number of cases was doing was growing exponentially.
Okay, good. Jill says the Richter scale. What do we use the Richter scale to measure?
Earthquakes.
Earthquakes.
What about the magnitude with tornadoes?
Okay, yeah, that I think you're right. I'm not as familiar, but I think you're right. When would we want to use the logarithmic scale, do you think?
Well, pH is used commonly because of the great difference between acidity and basis in the basic realm is so greatly different, but the magnitude really matters at a very specific point, especially in the human body.
Excellent. So did everybody hear that? So the logarithmic scales are going to let us look at things that have really big ranges of numbers. So if you look at your linear scale, what's in the very first linear scale, what's the range of numbers from 0 to
8.
8. But if we look at that logarithmic scale, the very first logarithmic scale, we go from 1 to
1 million.
1 million.
1 million. So if I'm looking at comparing measures that are going to be sort of close together, a linear scale is probably a good choice. But if I want to measure or compare things that are far apart, that's where a logarithmic scale is going to be really helpful. And so perfect example is pH, the Richter scales, those kinds of things.
Astronomy, maybe?
Okay, yeah, that would be a good, and we'll see when we look at the logarithmic functions in lesson 11, you're going to sort of be able to take a look at maybe why, right, some of those things, what they look like in 2D compared to what we're looking at in 1D here. All right, so I have pulled up here our Memoria page from last week, lesson 6, along with our Memoria page from this week, lesson 7. What is familiar and what is different? Or
It looks like the first column's the same, at least in the beginning.
so our general topic is the same, and we see that when we're looking at those laws, we see that those laws, right, at least initially are the same, but then we add some in, don't we? We add some other ones in or change some other ones when we're dealing with roots, exponents, and logarithms. So what are the 3 operations that you think we're going to look at this week?
The root, exponents, and logarithms.
Roots, exponents, and logarithms. Excellent. And so we're going to find out that if you become really confident and comfortable with how to switch between roots, exponents, and logarithms, we're just taking these laws and we're expressing them differently, but it's the same basic law that applies when we're looking at this, right? Just like it did, for example, for addition and subtraction went together, and then multiplication and division went together. We're going to see this blending of the ideas of roots, exponents, and logarithms. Are there any laws on there, especially in their expression, or if you look at the columns, is there one that seems more familiar to you than another?
Identity.
Good.
Well, product.
Good.
The 0, I think we saw in ex nihilo, that row.
Yep. Good. So there's a few things on here that maybe feel familiar. And these are 2 pages, right, that are chock full of symbols and notations. And so this is another place where maybe covering up some things for your student, especially if you think we're going to start working on adding some of this to our memoria in an intentional way, covering up some of this and just focusing on it so that they don't try to look at the whole page might be a strategy here. Copying these, some of these may be a strategy, limiting what you're trying to add to the memoria each time may be a strategy. For some of these, I think the exponents feel a little bit more straightforward than for other things. And so I may start looking at those laws for exponents first, and then look at roots and logarithms. So there's lots of approaches that we could take here with our students, but these are going to be some really practical. So where our laws for addition, subtraction, multiplication, and division are important, and we use them a lot, some of them can feel obvious and maybe a little bit trivial sometimes, right? Well, of course, number minus itself is 0. We think that, right? Do I really need to know the law? Whereas the laws for the exponents, especially where we're looking at the products and the quotients, the reciprocal, for example, the powers, that they're actually going to help us to manipulate and calculate with our exponents and roots and logs. So there's a little bit more, they feel to me anyway, a little bit more applicable sometimes in terms of what I'm doing. They're not more important or less important in terms of understanding why math works, but they are definitely important in understanding sometimes how to simplify and work with powers that are written in the form of a base and an index.
Kirsty, do you mind reading, so where it says laws and then it has the roots, exponents, logarithms, how would you read those three formulas or whatever that are right underneath? Like the first one, roots, base equals.
Sure. So I would read that as base. The base is the nth root of the power. The power is the nth power of the base, which I know I just kind of used like the word twice. I'll be honest with you, and I'm going to talk about this in a minute. I would also say, just because you all know what I'm saying, be that the power is the base to the index. But we're going to talk in a minute about how that language has done us such a disservice.
Yeah.
And I'm really trying to get rid of it in my vocabulary. And then the last one is that n is the logarithm base with the base of p, or my power. So I'm going to go ahead and take us to the next slide, because I really, I'm going to take a minute sort of out of our normal where we look at the charts together. I really want to talk about this idea of the threefold relationship. Of all the things that I've worked on in the math map, and there's a lot that I've learned. Like, I want to be really clear, I've learned so much. Probably my favorite, most personal thing that has resonated with me is a fresh understanding of powers. And here's when I said we've been done a disservice. That for years, let me make sure my pen is on. For years, right, we have all sat in classes. And if you've recently Googled this, you're going to find tutoring websites that do this too, where the teacher said 4 to the third power is 64. And if you're like me, and probably that teacher, we all thought this was the power, right? Because of the way we say it, the third power. And that's where we've done this huge, great disservice to generations of students, because that is not the power. This is my power, or this is my power. It's that entire expression, right? 4 cubed, that entire expression is the power, or the value that it equals, right? So this or this, the whole thing is my power. Okay. The 4, so I'm going to write here, power is 64. The 4 is my base. So all of you who have been wrestling with what do we mean when we talk about base 10 or base 2, this is exactly where it comes from. It says that this is the number off of which I'm building all other numbers, right? So in this case, 64 is built off of 4. My 3 is my index. And if you think about an index, is the thing that puts things in order, right? If I think about my powers of 4, my 0th power of 4, right? So my, right, is 1. My first power of 4 is 4. My second power of 4 is 16. My third power of 4 is 64. My fourth power of 4 is 256, and so on. Notice I'm writing these from left to right. When we were looking at place value, we started from the right and we went left. But it's the same thing, is that I'm simply expressing these numbers in terms of a base and an index. Yeah, so that's right. So it's only when it's in this position that it's called an exponent. All right. So when I have it written like this, base, index, power, right? That index is called an exponent. because it's using exponentiation, or exponents are my operation. So that index, because of where it is, it's telling me I'm going to use exponents or exponentiation to calculate my power. And so we're not defining, right? So that number in this case could be called the index, or it could be called the exponent, because of where it is, right? The exponent is where it is. The index is the job that it's doing in terms of the relationship. So base, index, and power are nouns, and the operation that connects them is exponents. When we talk about multiplication and division, right, flip-flopping or addition and subtraction being inverses of, there's two things. We're going to see here, there's three parts of this relationship. And I think maybe that's why this meant so much, was because I'd never seen that threeness before. But because I love God and the Trinitarian nature of God, I've started being a lot more sensitive to where threeness exists. And so God really, I remember the day that he was like, look, this is how this goes together. That the light bulbs all went off for me. Historically, we teach children about exponents, then we teach them about roots, and they get pretty good at that. And then for about 2 weeks in Algebra 2, in your sophomore or junior year, you learn about logarithms, and you never really understand what they are. And you just move on because you go, okay, and then you never deal with them again. And so they're this thing that's kept out here on the side. But when we realize that they are intimately related to exponents and roots, and to this base, index, power relationship, all of a sudden, to me, it just made so much sense, and I was really happy. And so that's why I'm sharing it with you, because to me it's so powerful for us as parents. For our kids, we can teach them this from the get-go and they're not going to be like, oh wow. But if you're like me as a parent, we're finally connecting things that we're taught as separate concepts, and we're finally bringing them together and going, oh, that's all that is. Because notice, if I understand my power is a base with an index as an exponent, well, I can rewrite this as my base is then I'm going to write index small, right, is the root of the power. And so this is where I'm using roots as my operation. And then right, notice I've solved for my power and I've solved for my base. So now how do I solve for my index? Well, my index, that's where the logarithm comes in. And so I have it written, right, that logarithms are my operation. And so one of the things you're going to see in the lesson pages is you're going to be able to take something like 4 cubed equals 64 and rewrite it. So if I wrote 4 equals, take a minute and think about what that would equal and how we would write that as a root. Right? It's the third root of 64. All I'm doing, same 3 numbers, I'm just moving them around. And if I wanted to write the logarithm, right, what is my index? My logarithm with my base, that's 4. And then my power, that's 64. So with our students, we could just keep, right, give them these in any of those and say, okay, write the other 2 expressions. This is like, to me, this is a really big thing. If this is the only thing that you get from this week, right? If this is the only thing you get from this week, I think this is is really a huge thing of rewiring our brains to understand what a power is and to understand how the power, the base, and the index are intimately connected together. Any questions?
I have
Yes.
one question that I think might be easy to answer. I'm sorry, I don't think I knew my camera was. Really quick. So my kids are saying 4 to the third power and 3 to the third power all the time. Is the correct way to say it? I would correct them and say the third power of 4.
That's how I am trying to say it, because I think, yes. And like I said, right, we've all talked this way. And so I'm not going to sit here and say I never say 4 to the third power, because it's just become how we talk. But it's really, I think, reinforces and misleads as to what the power is. And so I am really trying to change that and say the 0th power, the first power, the second power, the third power, the fourth power, because it also, when we do that, right, it helps us to see that this is what we're talking about, right? So for all of you who are going, okay, base 10, well, now do you see, just it went the other way. We had the 0th power of 10, the first power of 10. We just put all of those powers in order, going the other direction for place value. That's all we're doing. And when we use the index actually as an index, like it, I think, helps connect those ideas a little bit better in our brain. Amber, you could say an index of 3, if that's however you guys want to read it, think about it in your families. I would just really emphasize, right, that index and exponent are 2 different ideas, because index is that number that is going to stay the same wherever it is in this relationship, whereas exponents are specifically an operation based on the position of the index.
Could you re-say the noun? Like you said, I don't know.
Yeah, so base, index, and power, those 3 words are nouns that describe the parts of the relationship.
Okay.
Right. And then exponents are the operations that reveal the power. Roots are the operation that reveal the base, and logarithms are the operation that reveal the index. Jill.
And that's different from multiplication, because you're talking about 2 factors that have the, they're interchangeable in a sense, where you could do 4 times 5 or 5 times 4 and get the same thing.
Correct.
But the base and the index are in a different place, and they use they mean different things, and they're not interchangeable. So that's why you have to say power, or power is the end point of.
Correct.
Okay.
So when, in the first example, when we started the conversation and you said 4 with an exponent of 3 equals 64, that both parts, both sides of that are the power. The 4 to the third and the 64 are both, the whole thing is the power. So is that only in that setup? And then when you are looking at B equals the nth root of P, that is not 2 examples of power anymore. Now you're talking about base. So I just want to make sure I'm getting that part right.
Yes. So I could say, looking at the nth root of a number is giving me the base of that number, right? So that whole thing is the base.
Okay.
We just don't oftentimes think about it that way, right? We don't.
Right.
But it's just like saying, I could say that I can write 3, I can write 3, I can write 3, right? They all mean 3. So whether I'm talking about 4 cubed or 64, they're the same value, and it's that value that is the power.
I like that. That helps me. I mean, I think that was an aha moment for me, and I've heard you give this beautiful illustration several times, but just recognizing that scenario and then another scenario, the whole thing is the value. Thank you. I appreciate that.
All right. Any other questions or thoughts? I don't expect this to necessarily sink in and everybody to sort of have a light bulb moment, but I'm sharing with you my light bulb moment that I still get excited about.
That is super exciting. Sorry.
It is.
I wanted to ask, what if you start with a number that is not like what if you're not working with whole numbers, I guess? Like I
I'm
understand
gonna
with
go
64. Yeah.
I'm gonna go to the next slide just because it's blank and it gives us more work, right? My base can be anything. So I was thinking, I gave this example to Babs the other day. She was asking me about something. I'm currently knitting a blanket, and I'm essentially using base 18. And so this is what I do is I count, right? My repeat, I count, hang on, let me make sure my thing's on. Is I count, I have 18 stitches, right? So I do my pattern of 18, and then I count 1, and then I count my pattern of 18, and then I count 2. So I'm not counting, I don't even actually know. I think I have like 140 something stitches. I don't know, because I never count to 140. I count to 18 and I go 1, 18 and then 2, 18 and 3. So that's essentially base 18 that I'm counting, and I count up to 9, and then it's the next row. And that's the whole thing is I base 18 because I count up to 18 and 1, 18 and 2. But here's another thing. So when I went through a phase, my husband says I go through lots of phases. He thought homeschooling was going to be a phase, and it wasn't. So when I went through my bread making phase, because of the container I kept my flour in, I used a 1/2 cup measure. And so I was using like base 1/2, right? Because I would count 1/2 and then 1, and then, right, but I would essentially count instead of this. So this is really what my bases were. So I would have 1/2, right? And then it's a little bit different because it wasn't necessarily powers, but it's the same idea, right? That I was just counting my halves instead of counting. So I was kind of looking at multiples, I guess, not powers, but that same kind of idea. If you think about this, really 1/2 is a power of 2. And so if I was to be using 1/2, right, here's my 0, here's 1/2. Really what I'm doing is in base 2, because this is what I would think of, right, is that this is my -1 power of 2. Now I could have written it the other way and said that I had 1/2, and then but notice what happens as soon as I do this. I have 1/2, then I would have 1/4, and so it flip-flops. So it's probably easier to think that when I'm looking at a rational like this, that it's to flip it the other way and recognize that 1/2 is that -1 power of 2. And that way my powers line up bigger to smaller the way that I want to see them. Yes, cubes are the 3rd power of a base and squares are the 2nd power. Yes. But what I'm saying here is if I wanted to count by 1/3, or if I was working with 1/3, right, I might actually think of it as 1/3 being the -1 power. I apologize. Right, that this is the -1 power of 3. So I may still think of it in terms of base 3, but looking at it in those fractional pieces, which would make more sense to why if I was using 1/2, right? Because now when I count, what would I end up with? I'd end up with 1, and then 1.5, and then I would end up with 2, and then 2.5, and then 3, and so on. So if I was counting by halves, I'm still really in base 2 because I still want to be moving left to right but I'm starting at that 1/2 now instead of the 1. Did I confuse everybody there? Because I was sort of working that out as I explained it.
My question is, when you were giving us that definition of base, that 4 is the base. And now, oh boy, this is hard. So when we're talking, that operation is still in a quote unquote base 10, right? It's 0 through 9. So then how is that word base different from when we're actually talking about counting in a base 2 or a base 3 or a base 4 or base 18?
So it's really not any different. I'm going to erase this and so it's not any different. It's just the application of it. So, right, if I say 4 cubed equals 64, right, I'm just talking about, hey, I'm working on this operation and my base is 4, my index is 3, and 64 is my power. And I'm just operating on that. Whatever it is that I'm trying to do, I'm just using these numbers in this way to operate. Place value says I'm looking at all of the powers of 4, and I'm going to write numbers using all of the powers. So here I'm really just interested in the third power of 4. If I was looking at my place value, right? So I've got my 0 here, and then I would have my 1 here. If I'm in base 4, notice here's my 0th power. Here's my first power. Here's my second power. And this is just an arrangement of all the possible powers of 4, all the integer powers of 4. -1, right? The -2 power, the -3 power. And so I arrange them this way. And now I can say, okay, as numbers, right? This is my origin. So this becomes as numbers here. And the value of each place is defined by this base, right? So it's taking this idea of a base, right? And if you think about, when you say, well, what did you base that on? Well, what is it, the underlying facts that you based something on, right? That's the same use here, is what am I building my numbers on? I'm building them on a base of 4. And so 64 is built on the base of 4, right? It's the third power of 4. But when I line them all up, I can say, okay, well, now I'm going to define the values of my places using all the powers of 4, right? And so now my place value is based on this foundational number of 4. And so it's the same idea, it's just how we're using it is a little bit different.
Kirsty, I have a question about this line, base 4 line. So naturally, we are used to look at the line, number line based on smaller one on the left side and then bigger one on the right side. What is the purpose for you to lay it out? Even the negative, naturally we would look at the negative is on the left side, right? On this line, you don't have any negative, but negative power make me more comfortable on the left side than the right side. So what is the reason you line up like this?
I think, so I've used the illustration with some other people, this idea of buckets filling, right? And so I think,
okay, yeah.
I think it's just this idea that if I was to start filling my buckets, right? Let's say I started filling my buckets here, right? I'm going to start filling my buckets on the right-hand side. And as they overflow, right, they've got to go into progressively bigger buckets. And so I don't know why we write our numbers this way. I'll be honest with you, right? Because somebody said this is how we're going to write our numbers, so that our very smallest number in our place value system is to the right, and our very biggest number in our place value is to the left, which is a flip to how we see them on the number line. I don't know why. We just do.
But it is makes sense because in the computer science, when we do code, it's lining up this way, right? You fill it up on the left, right side, and then when it increased, move to the next base, is go to the
Yes.
left side. So yeah, thank you so much.
You're
But this is,
welcome.
would it be fair to say that this is kind of a different number line? This is a place value number line as opposed to.
Yeah, I didn't really mean to. I did not do a good job of writing it as a number line, and I apologize if that threw anybody off. I was just trying to like give that idea that these numbers are going infinitely, but this is approaching 0 down here, and this is approaching, right, infinity up here, all as powers of 4.
Gotcha. Okay, I would like to go back to the logarithm and just one question. The third equation that includes the word logarithm, that it doesn't just move the other 3 words around, it adds in the logarithm as the operation that is being done to look for the base or to look for the index.
So exponents, right, are the position, right? We know it's an exponent because of its position. Our base, right, we're looking at roots, which gets the radical symbol, right? The radical is what's telling us to do the root. And then our index is the logarithm is the operation, and the symbol for it is that log.
Okay, I have to think about it. I'm sure that's clear, but it'll take me a minute.
Yeah, because it feels like it's another word. But if you think about it as really, it's a symbol for logarithm, and not the word, then it's kind of like that radical. And then the exponents is the one that is this positional indication that sort of leaves us feeling a little bit uncertain, because you're like, well, where's, that's why we conflate the idea of index and exponent so much, because they're both in that same place in this expression.
Okay, thanks.
All right.
I have a question back to bases.
Yep.
I was explaining to my class my aha moment with the bases of understanding. It goes, 1, 2, 3, then we start back again, and 10, 11, 12, 13. And so they looked at me and said, well, what are we ever going to do with base 4? And I was like, I don't know. So this is how it connects, by base 4 having an index. Is that how?
Yeah, and I'm not going to give you a good a really good answer for, when are we going to use base 4? When are we ever going to use having read Shakespeare, right? There are things we learn not because they're going to be useful, but because it's going to teach us something about the structure, right? And so understanding this, how bases work, and then how we can use those powers to that our place value system is all based on powers. And so in order to know what the powers are, we have to know what the base is, right? Because it's all based on that base number. And so understanding that everything we do is based on 10, we understand that better when we look at it if it was based on 4 or 6 or 16. Some bases do have practical applications, especially in the computer world. Or like I said, when I'm knitting, right? I never knit to however many stitches I have. I'm working in base 18. I just count to 18 and I have 1, and I count to 18 and I have 2. So there's a lot of times that we use bases without even really realizing it, right? So you
So
might
is
tell
time an example of that? 60?
absolutely, yep.
Okay. Okay. That helps me because as you were counting to 18 and you said one, I remember laying on the floor counting 10 minutes in my head, 60. Okay, one, two, you know. So
Yeah, I
okay.
mean,
The other,
we do
the
it
other,
a lot but we don't even realize we're doing it.
the other thing I say to kids when they say, when are we ever going to use this? Is I go, well, if you go work out, you don't walk around saying, when am I ever going to walk around with dumbbells in my hand? Right. There's the process that you're learning to build up a muscle to do something more.
Oh, and when you just said that, it made me think about, right, how many exercises do you do in base 4? Right. And we kind of, and I'm going to say this, we mix up our bases, right? We may use our bases and then we go into base 10. But right, if you're lifting or you're doing jumping jacks, right? Let's say we're doing jumping jacks, you might go 1, 2, 3, right? 1, 1, 2, 3, 2, right? So we're counting in a different base. And like I said, right, or in music or anything
Well,
else.
yeah, that just made me think of time measures when you have 2/4 time or 3/6 time, or you have different bases. That's so good.
So yeah, so think about all the things that you do around the house that you don't just count from 1 to whatever you're doing, but you break it down, right? You're essentially using a different base because you're counting out, right? Maybe you're doing cupcakes and you don't count 12, you go, I've got 1, 2, 3, 4. Okay, do the next 1, 2, 3, 4. Do the next 1, 2, 3, 4, right? So that's essentially what a base is doing. And we don't maybe recognize that because we're not always going to 4 squared and 4 cubed. We're just using that first power. But that's what we're doing when we shut it down and we don't count to 10 and on. Um, we're we're bringing this idea of bases in.
So I'm really confused as to the difference in between multiplication and exponentiation in terms of the bases, because it sounds to me like we're counting by 4s, we're counting by 3s, we're counting by 60s in terms of minutes. So I'm getting the two mixed up in my mind.
So, and I probably am not helping you because yes, that's where I say we kind of conflate the idea. If I'm counting by 4s, but so yes, right. So I could say with my 18 stitches and I have 9, I could do this and I could say, okay, well, that's whatever that is. And I'm essentially converting that into, when I convert this to base 10, I'm using multiplication. Right now I'm using multiplication to find out what my total is. But when I just say, okay, this bucket has 18s in it, and I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And I count and then I go, I've got 1. There's the difference. And it's really subtle. It's a really subtle difference because when we're just using that first power, it's we're kind of, that's where I said, it's this idea of a base, although we're not necessarily using it perfectly as a base, we may switch to using it as a multiple because we then want to convert it. But it's just that idea of that first power of limiting something and counting by that, right? I'm counting by 4s. And I'm trying to think how I can, once we move into place value, right? Again, right. So here's my 1s, my 4 to the 0 or the 0th power, right? And this is where it breaks down because I probably wouldn't go, okay, I've got 116 and I've got, right, but I could. So if I said I've got 3 4s, right, 3 here, and then once I got to, and I skipped the first power of 4 here. If I said, okay, I've now got 1 4, and then I kept counting, and then I said, okay, I've got 16, that would be a more perfect case of using my place value in base 4 versus if I just said I'm counting by 4s and I've now got 10 4s, well, that's 40. That would be more multiplication. So I'm using that as a trying to just give this example for kids, especially when they're going, when do I use these different bases, to help them see that when I'm limiting it and I'm not just counting progressively, that's this beginning piece of where I would be using my bases. And I'm really sorry if I've inflated things in people's minds.
So this is the same as when we were working with base 10, base 2, base 3, but we're not limited to only using the number smaller than the base we're in when we come up with our final number. That's why we can have the 64, is because we don't have to stick to where we could only have 0, 1, and 2. And then,
Yes.
okay.
Yes. So that's exactly what, because these numbers here are how many of each of those, right? There are how many 64s do I have? And if I'm in place value, I can only have 3 64s before I would need to go to 256. So that's the difference between the place value and just using this as a base index and power relationship where I'm always working in base 10. I just want you to see that that's why we call it a base in that place value relationship. So the place value is an application of this broader idea of base index and power. All right. So I know that you guys probably are all like, she's confused me. And because this is a really big idea in math that we have not historically taught well. And so we've left all of us, right? Even those of us who have gone on and done graduate studies in mathematics, right? We know how to use this, but we don't really understand it. And so don't expect to understand it all today. If this is your first time hearing these ideas, and we can talk about it again next week on our book club there. So I'm not going to spend a lot of time because we're already past time, but you're going to see here looking at your lesson pages. We're not going to be getting into these really deep thoughts here. They are going to practice rewriting, but they're also going to be reminded to look at linear scale and logarithmic scale, right? That we're constant difference versus constant ratio. And then noticing that what happens with our hops once we get to exponentiation is our hops change size. So where in multiplication and addition, we had the same size hops, right? In addition, we had 1, but it was that size. In multiplication, we could have many hops. They were all the same size. And then in exponentiation, our hops get bigger. Here we're going to be looking at, here's an average. This idea of average isn't necessarily something that's in exponentiation, but you're going to see occasionally Lee brings in these ideas to fit them into places. And so as we look at exponentiation, we're really focusing just on simplifying some of these powers, right? So simplifying 2 squared is 4 and 8 squared is 64 and so on. So the operation may not be exponential, but we're going to practice simplifying those exponents, simplifying those powers. Don't forget all the resources that your students have just in their booklets and in those materials, the flashcards and the companion, that we're here for you. So next week, we're going to be wrapping up 1D, looking at equations, and then moving into 2D. So I had somebody this week say, what do you mean by the 2D lessons? So remember that the math map is broken up by dimension. So lessons 3 through 8 are all just looking at arithmetic on the number line. So there's a lot packed into these weeks. There's a lot packed into these weeks. I think as we move into the second dimension, it spreads out a little bit more. There's still a lot in there, but we're going to find that there's going to be some more restful weeks. So if you're kind of treading water still, and you're like, okay, when do we get through this? I really think you're going to find that when we hit the second dimension, lesson 9, that you're going to get a little bit of a breath, and you're going to find that there's more restfulness woven into the curriculum. And so I'm going to go ahead to a blank slide. And if anybody still has questions, I am happy to hang out for a few more minutes to answer those questions. But I also want to honor your time. And so I will say thank you for being here. And again, I'm here to answer questions if you guys still want to talk through some things.
Could you explain the anything to the power of 0 equals 1? Again, I have quite a few parents that keep asking about it and referring to it, and I have a boot camp coming up soon, so I would like to be able to explain it in some type of general high level. So, because some of them are saying, well, my kid's using it, but they don't know what they're actually doing or what it means. Yes.
All right, so I'm going to show you 3 ways. So if anybody's heard me talk about this before, we've done 2. I'm now going to give you a 3rd way. So one way is if we just think about exponentiation, and I'm going to write it vertically so we can see the pattern. If I have, let me make sure that my pen is on. If I have 2 cubed, we know that that's 8. If I have 2 squared, 2 squared, that's 4. What did I do to go from 8 to 4?
Divide by 2.
I divided by 2, right? And if I went the other way, what would I do to go from 4 to 8?
Multiply by 2.
Multiply by 2. So this is our vertical pattern, is we're dividing or we're multiplying, depending on the direction we're going. So now let's look at our exponents. To go from 3 to 2, what did we do?
Subtract 1.
Exponent? Yeah.
I subtracted 1, right? So this is, I'm going to put here power. And on this side, I'm going to put index. Notice my base stays the same. I'm not going to mess with my base. My base stays the same. So if I'm going down, I subtract 1. What if I'm going up? What do I do to my base?
Add 1.
I'm going to add 1. Okay, so now let's go down another level.
Did you say your base to your base?
My base is always 2. I'm never going to change my base, but I can change my index. And then when I change my index, I change my power. So in this case here, right, I'm going down. So I'm going to subtract 1 from my index. I'm going to divide here. Sorry, this should be 2 minus 1, which is 1. I'm going to divide, which is 2, right? So this is the first power of 2 is 2. So now I'm going to go down another level. And so 1 minus 1 is 0. 2 minus 2 is 1, or 2 divided by 2 is 1. And this pattern continues because if I keep going and I keep subtracting, I'm going to keep dividing. So I'm subtracting my index and dividing my power. Subtract 1, divide by 2, subtract 1, divide by 2. And that's my pattern. And I can go the other way, right? And so if I go up, right, 1/8 times 2 is 1/4. -3 plus 1 is -2. I can go up another one. -2 plus 1 is -1. So I've got the negative first power. 1/4 times 2 is 1/2. I can go up another level. -1 plus 1 is 0. So now I've got the 0th power of 2. 1/2 times 2 is 1. Okay, so I've just written it this way so you can see this pattern of my index goes up or down by 1. That's sort of linear. My powers go up and down by a factor, right? So my index is linear, but my power is logarithmic, right? Those scales that we're seeing there as we write it that way. But right in the middle, we see that the 0th power of 2 is 1. And I could have replaced this with anything. Right? I could make this the base 3, 10, 49, pi, whatever it is. My index is still going to go up or down by 1, but I'm going to multiply or divide by my base. So that's one way of understanding it. Another way of understanding it is to remember that there's this hidden 1 that we don't write. So if I think of 5, what I'm really saying is that there are 5 1s. If there's 7, it's really 7 1s. If there's 7 squared, well, there's 7 squared 1s, right? Which I could say is 7 7 1s. So 2 cubed is the same thing as 2 times 2 times 2 1s. And so if I was to write 0, so notice here I have 1 factor of 5, 1 factor of 7. I have 2 factors of 7. I have 3 factors of 2. So if I have 0 factors of 2, I still have this 1 here. So that's another way of thinking about why it is, right? I'm saying there's 0 factors of 2, but I still have that hidden 1 that's out there, which is how we understand this to be 1, because I'm saying there are no factors of 0. And so I'm still left with that 1. And then, again, just going from what we were talking about today, right? When we think of our powers, right? My first power of 2 is 1, is 2. My second power of 2, my third power of 2, this is 2, this is 4, this is 6. So my 0th power of 2 is going to be my 1, because my negative first power of 2 is my 1/2, which is similar to what I've got written vertically. But just here, seeing them written this way helps us to maybe connect that to our place value, right? So here are my powers. When I write it as place value, remember that I have on this side my negative powers, and then my 0th, my first, my second, my third for my places. And so this has to be, my 0th power has to be 1. It has to be the unit, right? Because I count by my units. So it has to be my units when I look at it here, in my place value idea. All of these are really saying the same thing. They're just different ways of writing it out to show that that 0th power is 1.
Thank you so much. And I don't know if I can do this without crying. I really appreciate what you are doing, because all my life I have said, well, I'm just not good at math. And it has made me realize getting to do this, and I don't even have a student going through this. I'm just doing this as a challenge aid director, but it's made me realize how much of God I have cut out of my life by saying I'm not good at math. And so I have pushed away a whole side of his creation because I was cheated by not knowing this, because they taught us everything in boxes and separate from things and didn't relate anything back to God. So I'm so appreciative of what you're doing.
Well, thank you for that testimony, and amen. Yes. I think we all have that experience, whatever it was, right? That we were taught. I shared with somebody the other day, like, I had my academic brain and I had my God brain, right? And I believed everything I was taught about the Bible, that there was creation and this, but I also believed that the dinosaurs lived billions of years ago. And we had a biblical paleontologist come to church one day, and my worlds crashed together. And I realized that for decades I had held 2 separate brains, right? And that I had somehow kept them separate. And God suddenly said, no, you have to you have to put these together and see me in all of it. And so, um, right, Satan just wants to keep us from knowing God. And so he's going to use whatever lies it takes. And I just praise God that you are embracing finding him in mathematics. So thank you for that testimony.
I have one more question / idea about this x to the 0 power equals 1. Could you also do, like, we know that anything over itself is 1, right? So 2 to the third over 2 to the third is still 1. And the way we solve something like that, I'm thinking, is 2 to the third minus 3 still equals 1. So the 3 minus 3 equals 0. So 2 to the 0 equals 1.
That's exactly, yeah, that's exactly right. Yep.
Okay, thank you.
Any other questions that we can answer or work through for anybody?
So, Kirsty, I had a question about just application of the like the 5 common topics as we're going through the booklet.
Yep.
I'm getting to the point to where like I tried to train my families and my own kids, like as we're going through, like, what are you being asked to do? Like, do you understand the instruction? Can you do that instruction? Just as a way of not getting overwhelmed with everything on the page. And so I feel like we've gotten to where they're doing that, and now they're kind of saying, okay, so I was able to figure it out, but I don't understand why. And so, like, particularly like with the conversions, summations, and then we're just getting into factorials, like it feels like if they can do it, then kind of that next step of why is learning the rule or the skill of how to do that. Like, am I interpreting that right? Like, I'm just like, if they can do it, like, I'm just trying to wrestle with, like, when do we like dig into the skill that they're supposed to be learning how to do, as opposed to
Right.
just like can like with the conversions, like it has all the conversions set out for you. All they're really doing is multiplying fractions, and they know how to do that. But at what point do I press in and kind of go, okay, do we know why they set it up this way? Like, do you know what I'm saying? Like,
I do.
it's just
So
attention.
So we know that we've got our grammar stage, right?
Right.
And this is where we're going to be naming things. We're going to be expressing things, memorizing things. We're going to be using the right words. And a lot of what we're doing this year is that grammar stage.
Right.
We've got this dialectic stage. And we think of this, right, as our common topics, are our skills, and we're thinking through this, and we think of this, right, as our knowledge, and our understanding.
Mhm.
Now I just want to, and I'm going to put down here, we've got our rhetorical stage.
Right.
And our canons and wisdom. There's a big gap between dialectic and rhetorical. Because our dialectic, I can understand something and not be able to tell you how I understand it.
Right.
Right. I can go, oh, I understand why I did that. Well, why did you do it? I don't know. Well, because that rhetorical is getting that to that point where I can now tell back what I did. And so, one, encourage your parents that they may be beginning to understand things, but the fact that they can't express that back is not an indication that they're not understanding it yet, but an indication that they're not rhetorical yet.
Right.
Right. So there's this big thing. Then the other piece of it is that there's this idea in here that we're going to be moving from the concrete to the abstract. And we're going to be making these generalizations. And I think that's a little bit at what you were getting at, right? So I could say, can you add 1/2 and 1/3? And a student might go, yes, I know that that's 5, 6. I've memorized that fact. Then their next thing might be, okay, well, I know that I have to make these into 6. And I maybe don't even fully understand why. Right, 3, I can do math. 3, 6 plus 2, 6, right? They might not even fully understand why, but then they go, oh, because my denominators have to be the same, right? And then at some point, they get to this point where they go, oh, well, look, if I just have 2-unit fractions, I can do this. And oh, sorry, this is A over AB. And I know that this is the generalization. Now, this could be grammar for some students, right? They might just memorize that. But there's this progression where I know the grammar. Okay, now I can pick it apart and I can say, this is what I'm doing with numbers, and I can solve things with numbers. And then at some point, I'm going to see this pattern and I'm going to go, oh, the pattern is just this, right? That if this pattern always holds true. That's when I would say you're really getting into that depth of understanding where you're becoming rhetorical. Now, for some students, depending on their background, right, you might have students that are still in that very concrete, let me memorize the fact. And you probably have students who are going, okay, I understand why this works. And then fewer students are now making that generalization. So this year of the math map, the complex is not trying to guide anybody to that generalization. It's really trying to emphasize that grammar and show enough patterns so that we're developing this pattern finding habit. And maybe we're not generalizing those patterns, but we're recognizing the pattern to say, so for example, on that way back in booklet 2, where it was writing things with it was like this 4 plus 0i, and so then they had to write 5, and they had to recognize it had a 0i. Oh, here's my pattern, right? So the goal this year is really to start looking for those patterns and use those patterns to answer things, even if they don't know what the generalization is. Sometimes you're going to see that generalization, sometimes you're not. But even when we're looking at the laws or right applying those things, we're kind of crossing that bridge a little bit between the concrete and the abstract, but we're still trying to look at very concrete applications of those laws. So I can't really tell you easily like where to press in because it's going to depend on your kids, but does that help give you a sense of the pattern?
Kind of. I think, I mean, I'm seeing the pattern, but I think sometimes too, like, I'm not like with the conversions, I don't know how many booklets out are they going to not have that scaffolding and kind of know, you know what I'm saying? So like, at what point do I need to draw their attention to that so that they start to know, like, okay, like they're understanding, okay, it's 1, like because of the green box tells us that it's 1. So we're not breaking any laws, so we're not going to get into trouble. Um, and they're sometimes are recognizing the grammar of, okay, 12 inches is 12 inches is 1 foot, or 3 feet is 1, like, so they're recognizing the grammar. But the process right now is completely laid out for them.
Right.
And I just want to support them well so that like at what point, I don't know, like right now I'm just letting them lead me. Like if they ask the question, I'm going to show them how to do that and what's going on, and like we're going to use circumstance, like is there a different way we could have done that? Like some of them know like 36 inches is a yard, and we can do that in 1 step instead of 2 the way they're in the booklets, which is fun because then we can compare.
I think you're going to find that it's going to look like this. It is a gradual slope. It is a very gradual slope, and then I think it's going to go like this. So even with monomials next year, I think you're going to find that it's this gradual slope up, and then in challenge 1, 2, 3, and 4, it's gonna start ramping up as their brains are ready to do that. But yeah, I think even next year you're gonna find that there's a lot of scaffolding. And it may be over the years that there's more scaffolding than they need. But right now we're trying to make it very hospitable entry into this, and then that scaffolding is going to go away, right? A little bit each year, they're going to lose a little bit more scaffolding. But I think you're going to see that ramping up in the upper challenges.
Okay. So for now, just the kind of like, can you do what's being asked is sufficient. Like
Yes.
if you can, if it says simplify and you can simplify based on what's there, then we are golden. And
Yes.
it's just as the students are kind of going, okay, but I don't really understand why. Can you explain that? Like, and if I as a mom can do that, I can say, yeah, sure, let me show you how that works. And if I can't, we can kind of go, well, I don't know. Let's see if we can figure it out. Or I don't know. Let me see if I can figure that out and let you know next week, right? But that's all, that's okay. Kind of letting the students' level of inquiry kind of lead deeper when they're ready for it.
I think that's a perfect way to put it. Yes.
Okay. Okay. That's helpful. Thank you.
You're
And so
welcome.
also when I'm seeing like on this little thing, then so really the scaffolding starts to drop off when developmentally they're becoming more rhetorical. Is that
Yes.
right?
Yep.
Okay. Okay. That's helpful. Thank you.
You're welcome. All right. Any other questions?
I have a mama question. Like I'm a challenge A director, but my challenge 2 student was kind of struggling with math. So I just said, all right, we're just going to go back and do complex. But he's 16. So he really has 2 more years of adding, monomials and then the next one. So at that point, I mean, if someone's starting off even, I guess is he going to be ready to graduate? Do I add more things to it? Can I just do these next 3 levels with him and feel like he's consumed enough math to go to the next level?
So I'm going to give you an answer and a non-answer, right? Is that your son is going to see like all of it in 1 year, and then again and again going a little bit deeper, and using working with more algebraic concepts in the next 2 years. If your goal is for your son to have a solid grounding of what we think of as K through 12 math, a solid grammar of mathematics, a solid understanding of how it fits together and what all these concepts are, then I think, yes, you are going to hit your goals as well as you would with any other curriculum, probably a lot better. Because of that repetition, we're actually going to be developing a long-term memoria about math that conventional curricula don't. You may find that you want to supplement, maybe not this year, maybe in 2 years, with some more algebraic computation practice. So he's going to have a lot more grammar, but he may not, through those 3 levels, he may not get all of the computation practice that you might want him to have. If he's planning to go on and do sort of mathematics in college, I would say, especially that last year, adding in a little bit more, of computation practice may be helpful. Now we are close to finishing up the monomials, so I know what that looks like. Binomials is still in development, so I can't sit here and give you a perfect picture of what binomials is going to be. It is going to be emphasizing that algebraic computation, but you may want to add a little bit more in. So
Okay.
that's where it's an answer and a non-answer.
Yeah. That can I do the reverse our hat and say, sure, I've got a challenge new challenge student and they're in D, do we tell them to go back and do complex? When we have, and then in the future we have one student entering challenge for the first time and they've never done this, do we tell them to go back, or we just tell them to jump in where they are?
So
We haven't gotten there yet, I know, but
yeah, and I think that's where I think that's where you're probably going to it's going to depend on the student. Is that you might have a student. So the best, I mean, we keep saying the best way, the best entry is to work through the naturals because it's quick, it goes quick, and it introduces you to all the big ideas. It's going to depend on whether that student is coming from a background where they've already done some algebra, right? If they came in and they're like, oh, I really feel like I've got a solid algebra foundation, then they probably could just jump right in. Maybe do the naturals to come up to speed on the math map and then jump right in. If you have a student that comes in and they're like, man, my algebra skills are weak, then maybe you say, well, hey, why don't you try monomials or binomials instead of jumping into polynomials or expressions? The beauty of the math map is that whatever level they end up filtering into, is that they're going to be able to participate fully in community, right? Because it's going to be so similar. Once all these levels are released and they're in the companion, that's going to be a great place for a parent who goes, well, what is it what level do I need? That they'll be able to actually go and sort of preview those levels and look at those pages digitally and say, oh yeah, we could do this, we're ready for that, or oh no, this is going to be the one that's so I think that will help answer some of those questions for parents too once that's all released, because then they'll be able to see it and better have eyes on to adjust for each student.
Thank you.
You're welcome.
Kirsty, I'd like to share something what I was struggling. So I hope this will motivate a little bit the mom earlier. So I have a student, my daughter, she is using Shulman math, is a little bit advanced mathematic curriculum. And I have a son is really, I think like 4 or 5 level below his grade level. But he has his gift. He knows patterns. He knows the difference, but he couldn't do, or he still cannot do basic calculation, addition, subtraction, multiplication, division. I've been praying for curriculum, and math map was perfect for him because he can use his strength. Even though he cannot do basic calculation and he look at the pattern, he get excited. And some of the stuff, even my daughter can figure it out. He could just point it out because he can see the pattern. So I think math map laid out perfectly for all the area. For the student have a different gift, which we, as a parent, we couldn't see it. I have mathematics and computer science dual the background, but I couldn't teach my son because my brain didn't wire that way. But he used math map every day. He is excited, even though he copied the answer on all of things, but he has a confidence that I will do a math map. So I think a lot of things, even though we don't see yet, using just the curriculum, if the student excited about it, I think that's a win for homeschool mom or homeschool teacher. And I remember when I was in high school, I saw all these boys, how much they just grew so much. And I truly believe mathematics takes maturity, and the boys, they mature slow to a lot of time. And we, as a mom, all majority of the homeschool parents are mom, and especially have struggling boys. I think take your faith and use this curriculum and trust it. Maybe I'm pretty sure, just like what Kirsty you said, it will grow exponentially. And when they hit junior and senior year, it will blow our mind.
Thank you for sharing that. All right. Well, thanks everybody for being here, and I look forward to seeing you next week as we wrap up the first dimension.
Thank you.